Welcome back to another statics video. We're looking at chapter 6 in the textbook and talking about friction. So in the previous example problem, we looked at a situation where we had a box on a horizontal surface and we were going to apply a force in the horizontal direction, and we wanted to find out how much force would be required to make the box move, or just about almost move. In this example problem, we're going to apply this load P at a diagonal direction. So that means that our applied force P is going to have both a vertical and horizontal component. So if we start by summing the forces in the y direction, we have the 400 pounds, the weight of the box, going down. We also have Py, which Py is equal to P times sine of 30 degrees, the angle it makes with the horizontal. And that's also going to be going down. And resisting these two forces combined will be our normal force, N. So that's going up. Now we have two unknown forces here in this equation. We have P and we have N. So we're not going to be able to solve this equation and get a number. We're going to only be able to simplify it somewhat, or solve it for one variable in terms of the other. And so I think I'm going to solve this for N, find out what is N in relationship to P. So N is going to be equal to, and I guess up here I should have said all of this is equal to 0. Let's be accurate in our mathematical statement here. Sum of forces equals negative 400 minus P sine of 30 plus N equals 0. So now I can go about solving this equation for N. I can add these two negative terms to the other side and get 400 plus P sine of 30. And I can't really take it a whole lot farther than that since I've got the two unknown forces here. But I do have another equation I can use, and that is sum the forces in the x direction. So we'll just leave this equation here for now and move on and look at our forces in the horizontal direction. So what do we have going on there? We have the horizontal component of P, which we'll call Px, and the horizontal component is P times cosine of 30. So see, this stuff with the vectors, with the x and y components, this just continues to pop up over and over again. So you really need to make sure you're very comfortable with this idea of taking a vector and breaking it down into x and y components. Okay, so this is equal to P cosine of 30. That's the horizontal force Px here. And what else do we have? The weight is purely vertical. There's no horizontal component there. The only other force is the friction force. And friction is equal to the normal force times the coefficient of friction. And we were given in the problem statement that this is 0.4. So this is 0.4 times the normal force. And that's going to be going to the left. So we can subtract from that minus 0.4 n. Okay, so here's where we can take our equation for n and substitute it into this equation right here. Oh, and I should have written out that this is all equal to 0. So there's my equilibrium equation, P cosine of 30 minus 0.4 n equals 0. What is n? N is equal to 400 plus P sine of 30. If I substitute this in here, then we'll just have one unknown, and that unknown will be P. So I've got P cosine of 30 minus 0.4 times, be sure to use parentheses here, 400 plus P sine of 30. And that is all equal to 0. Okay, so I can start by distributing the negative 0.4. So p cosine of 30 minus 0.4 times 400. And then be sure to distribute both the 0.4 and the negative, so this is still a negative term. Negative 0.4 p sine of 30 equals 0. All right, this term here in the middle doesn't have a p variable in it. Let's just move that to the other side. So now I've got p cosine of 30 minus 0.4 p sine of 30 equals 0.4 times 400. So now I have two terms on the left here. Both of them have p in it, so I can factor that out. P times parentheses cosine of 30 minus 0.4 sine of 30 equals, I'll go ahead and simplify this. 0.4 times 400 is 160. So now, kind of running out of room here, now I can solve for p. P is equal to 160 divided by cosine of 30 minus 0.4 sine of 30. So now we can put that into our calculator, and I get 240 pounds. So you can see that by pushing downward on the box in a diagonal direction, we're being a lot less efficient than we would have been if we just pulled or pushed it in a perfectly horizontal direction. Because in part A, we found that the force that is going to cause motion to occur is going to be 160 pounds. By pushing in a downward direction here, we are not only making it less efficient because only the horizontal component actually causes motion, but by pushing down on it, we're increasing the normal force, which therefore increases the friction force, which just means we have to push even harder. So we can see that that 240 pounds there is quite a bit more than 160. So if we're trying to move this box as efficiently as possible, push or pull in the horizontal direction. Okay, so boxes on horizontal planes are fairly easy to deal with, but what if the box is on an inclined plane? That does make it a little bit more complicated. So here we have a problem, again, where the coefficient of friction is 0.4, and this time the box is on an inclined plane. The inclined plane or ramp makes an angle of 30 degrees with respect to the horizontal. So we want to figure out how much force will be required to move it up the plane. That's the first thing we want to do, part A. Part B, we want to find out how much force is required to cause motion down the plane. And in fact, what may be the case is that we don't have to apply any force at all. Maybe if we just don't apply any force, the weight of the box itself will cause it to slide down the ramp. We'll have to wait and see. And then we'll look at if the P force is 450, what is going to be the direction and magnitude of the resisting friction force. So the thing that can be a bit confusing about an inclined plane is figuring out all these angles. And I have come to the conclusion, really, that the simplest way of looking at this is to consider in this diagram here, with the inclined plane drawn at an inclined angle, just remember that gravity always works straight down, okay? So the weight of this box is going to be going straight down. Now, we weren't given the weight, we were given the mass. So I have to, again, remind you that only when we're given a mass of 140 kilograms do we need to find the weight by multiplying it by gravity. So we have 140 kilograms. We're going to take that 140 kilograms and multiply it by the acceleration of due to gravity, which is 9.81 meters per second squared. So when we multiply 140 by 9.81, we get 1373 newtons. Okay, newtons are a unit of force. So that's the weight, 1373. So the way I like to think about it to help alleviate the confusion due to the inclined plane is think, okay, so the weight was going straight down originally. Now let's take this whole drawing. Maybe this is on your sheet of paper. You just rotate your whole sheet of paper. We want to rotate it so that this surface of the ramp becomes horizontal. It becomes our horizontal x-axis. Okay, so if we do that, we're going to have to rotate the whole thing 30 degrees, which means this weight, this 1373 weight, which was going straight down, now it's making a 30-degree angle with respect to vertical. So the fact that the weight of this box is no longer vertical in this diagram here, now that we've rotated the entire diagram 30 degrees, that means that the weight has both a horizontal and vertical component. So we've got Wy and Wx. So the weight of the box is pushing perpendicular to the surface of the ramp, which is going to cause the normal force, but it's also pushing to the left, down the ramp, which, as I said, depending on what the friction force is, the box may just slide down the ramp all on its own. Whether or not that happens depends on whether or not this x component of the weight is greater than or less than the friction force. So let's determine the x and y components of the weight now. So Wx is going to equal 1373. Now the angle we have here, 30 degrees, that's with respect to the vertical, which is not the angle we like to use. We like to use the other angle, which is 60 degrees. 60 and 30 makes 90. So I want to use 60 degrees so I can use cosine to find my x component. 1373 times cosine of 60. And the y component of the weight is 1373 times sine of 60. So let me calculate those two values. So I'm going to round this one off to 687 to three significant figures, 687 newtons, and the y component, the vertical component, 1189 newtons. Okay, so if I look in the vertical direction, the sum of forces in the y direction will equal 0. What are those forces? I have the y component of the weight. Okay, so I have 1189 newtons going down. What else do I have? Only other thing I have is the normal force, which is going to push up against that force. So that's, maybe I'll just forget about the n for newtons for right now, because I don't want to confuse it with my n for normal force plus n. Okay, so that just means then that n is equal to 1189. If my normal force is 1189, then my friction force is equal to the normal force times the coefficient of friction. So the friction force is going to equal 1189 times 0.4. And oh gosh, it looks like I'm just about out of time here. So I'm going to have to resume this problem in the next video.